we're going to talk about integrals now. And by integrals, I don't mean the area under the curve, and I certainly don't mean an antiderivative. If you look in the dictionary, the definition of integral is whole, entire, intact. Integration is the mathematical way that we get whole quantities by breaking things up into parts and adding up the parts. So let me give you an example of what I mean. Suppose we want to figure out what is the population of Texas. Now, one way that you might figure out population is you can say, well, what's the population density? Is it really urban and very high population density, or is it very rural and very low population density? And then you take that population density and you multiply it by the area of the state, and you should get the population of the state. The trouble is that Texas doesn't have one density. Over here in Houston, the density is very, very high. Over here near Big Bend, the density is very, very low. There's no one number that you could use. So what do? How do you get a good estimate of the population of Texas if you don't know the density everywhere? The answer is you break Texas up into pieces. In this case, counties. Texas is made of 254 counties. And what you do is you figure out, well, what's the population of El Paso County? What's the population of Presidio County? What's the population of Travis County? What's the population of Harris County? If you can figure out the population of each county, then you can add them up. The whole is the sum of the parts. And it's pretty reasonable to try to figure out what the population of Brewster County is by taking the density in Brewster County, which is very, very low, and multiplying it by the area of Brewster County, which is pretty big. But even so, there still aren't a whole lot of people in Brewster County. But even within a county, the density can vary. Here's a picture of Travis County. In the middle of Travis County, in Austin, central Austin, the population density is quite high. Out by Lake Travis, the population density is much lower. So if you want to get a good sense of the population of Travis, you don't pick one number and multiply it by the area. You break it up into pieces. In this case, this map shows the voting precincts. You take each piece, you figure out the population of each piece, and you add them up. And in this case, you can do a pretty good job of saying what is the density of each piece multiplied by the area of each piece. That's the population of each piece. You add them all together, you get the population of the county. It's not exact, but it's pretty good. If you want to do better, you break things down into census tracts. If you want to do better, you break it down into city blocks. If you want to do better, you break it down even further. And of course, if you want to do it really well, you send a census worker to knock on every door and actually count the people. Okay. So there are lots of things in math that you want to figure out this way, and that you have this big bulk quantity, and you want to break it up into little pieces. It's not as complicated as doing Texas, which is two-dimensional. The things we're going to talk about are mostly one-dimensional. You get two-dimensional stuff in 408M. So the simplest example is area under a curve. So we have the curve y equals x squared, and we want the area under the curve, say, between 0 and 1. As you saw in the other learning module, you get this by breaking the region that you're trying to measure up into pieces. You've got a whole bunch of pieces, and you want to figure out the contribution of each piece. So the area of each slice is approximately the height of that slice times the width of the slice. I say approximately because it's not exactly a rectangle. Is the height this, or is the height this, or is the height somewhere in between? Well, when you slice it really, really fine, you don't have a problem. But if you, for any particular level of slicing, you still have a little bit of error. And then you want the total area. Well, that's approximately the sum of all of the slices of the area of the slice. And then if you want the exact area, that's the limit as n goes to infinity of the sum of the slices. and we have a name for that. We call that the definite integral of the function, and in this case it's the integral from 0 to 1 of x squared dx. Okay. What we're going to do next time is we're going to tackle a bunch of very different problems, and we're going to see that the exact same integral describes a lot of different things. In all cases, we've got a bulk quantity, we chop it up into pieces, we estimate each piece, we add them together, and we take a limit, and lo and behold, that's an integral.